Okay, we selected a conductor that has sufficient ampacity for our adjusted maximum circuit current. Now we need to make sure that the overcurrent protection device actually protects the conductor under the conditions of use, and we have to make sure that the conductor, while it's operating, isn't going to exceed the ratings of any terminals that it's connected to. Step 4. Does overcurrent protection device protect the conductor under conditions of use? Recall standard overcurrent protection device sizes in 240.6a, and 240.4b, which we hit on briefly, says that the next higher standard overcurrent protection device above the ampacity of the conductors being protected is allowed to be used. And we'll see that come into play here in just a second. Basically, if I have a wire that can really only handle 13.5 amps, the next standard size, the 15 amp breaker or fuse, is okay. The logic here is that, well, these things all have curves associated with how they operate. The trip curve, the time it takes for an overcurrent protection device to operate versus the amount of time it takes for a wire to suffer damage, and the fractions or a few amps that may come into play here when we round up that OCPD size isn't going to result in an unsafe condition. 240.4d, also something to keep in mind. Small conductors have maximum allowable overcurrent protection device sizes. Again, they may have enough rated ampacity or even corrected ampacity for the circuit. Doesn't matter if the breaker's bigger or the fuse is bigger than what's shown on the slide here. So 14 AWG copper can't be connected to bigger than a 15 amp breaker or fuse. 12 AWG copper can't be connected to anything bigger than a 20 amp OCPD, and for a 10, nothing bigger than a 30 amp OCPD. So keep those in mind for our small conductors. Above that there's not a stated limit, except that, well, the overcurrent protection device actually has to protect the conductor. So step 4, continuing with our example, does the OCPD protect that conductor? Our minimum overcurrent protection device size, which we calculated in step 2, was 15 amps. And we're using a 12 AWG THWN-2 conductor, which is rated for 30 amps. That's its rating per the National Electrical Code at 30 degrees Celsius. We can take that 30 amps and apply those same conditions of use factors to get a corrected ampacity for the conductor. Right? Previously, we took them and we adjusted the circuit current to figure out how big of a wire we need. And then when there was a little bit of roundup there, right, we didn't quite need all of the ampacity of a 12, so we rounded up a little bit. Now we'll take those same factors and kind of do the reverse. We selected this wire. It's rated for 30 amps. Under those same conditions of use factors, right, ambient temperature, 0.87 correction factor, 12 current carrying conductors, and conduit, 0.5 correction factor, that tells us that when we're operating this conductor that way, that's rated for 30 amps, under those conditions, it's only going to have an ampacity of just over 13 amps, 13.05 amps. Is that okay? Does our overcurrent protection device protect that conductor, which has a pretty dramatically reduced rating? And really, in this case, it's mostly due to the fact that we've got so many wires in a single conduit. Yes is the answer. 240.4b says you can protect a conductor with the next larger standard size, 15 amps. That was our calculated minimum. Our conductor under conditions of use has a rated ampacity, or a corrected ampacity rather, of just over 13 amps. It's okay to protect it with the 15 amp overcurrent protection device. Next up is device terminal temperature ratings. Just like wires, the things we connect those wires to, the terminals on them, they have a rating as well. And we do not want to exceed that rating because it can obviously cause damage. What's going to cause it to exceed that rating? Well, it's going to be because the wire is getting hot when it's operating, especially if we're pushing it towards its limit in terms of using all of its rated ampacity. So section 110.14c requires us to verify that the operating temperature of the conductor will not exceed the temperature rating of the terminals on the devices it's connected to. Rating of the terminal is going to be 60 or 75 degrees C most likely. Often you see that dual rating, 60/75. In some cases, you may see 90 degrees C rated terminals. Some of solar equipment manufacturers realize that that's beneficial and do that, but you're not necessarily connecting the wire to a 90 degrees C rated terminal on the other end, right? Maybe the terminals in the combiner box are 90 degrees C rated, but what about the disconnect switch? If they're not, then it doesn't really matter that one of them is necessarily. So very common to see that 60/75 degrees C terminal rating. You can see them on here. You can kind of read it on that breaker. It says CU-AL 60/75. So copper or aluminum and a 60 or 75 degrees C insulation rating. Can't really read it on that disconnect switch, but it says the same thing. And that's really most common for electrical equipment. 60/75 or 75 degrees C rated terminals. We're going to run into this all the time. We're going to be using conductors that have a 90 degrees C rated insulation, which means when we do our calculations, we're ensuring that they don't go above 90 degrees Celsius. But then we're taking that same wire and connecting it to a terminal that has a lower temperature rating. We need to make sure that the wire, when it's operating, is not going to exceed not only its own insulation rating, but the lower rating of those terminals as well. Okay, back to our example. Step 5, device terminal ratings, continuing with the PV circuit example. The idea here is that our step 3 value, right? What was our step 3 value? Think back. It was maximum circuit current times 1.25 or maximum circuit current adjusted for conditions of use, whichever was bigger. In this case, because of our conditions of use factors, our maximum circuit current adjusted for conditions of use was driving our conductor ampacity requirement. We're going to take that same value that we just calculated. We already know what it is. And we're going to say that that's got to be less than or equal to that same conductor's ampacity from the column in table 31016 that matches the terminal temperature rating. So thus far, we've been doing all of our corrections based on the rating of the insulation of the conductor. Now we're going to move over to the column that matches the rating of the terminal. If we're less than whatever the ampacity of the wire is in that column, then we're not going to go over that temperature and we're going to be okay. All right, so yeah, the bigger value, our step 3 values, either maximum circuit current times 1.25 or maximum circuit current with adjustment and correction factors. So we had 11.7 amps is our maximum circuit current, divided by 0.7 for ambient temperature correction, divided by 0.5 for those 12 current carrying conductors and conduit, and our step 3 value was 26.9 amps. Now, if we look at the table, 31016, and we go over to that 75 degrees C column, we see something bad. Something bad. That 12 AWG conductor, which has an ampacity of 30 amps with 90 degrees C insulation, well, connected to a 75 degrees C terminal, we can only run it up to 25 amps. If we go above 25 amps, the conductor temperature could exceed 75 degrees Celsius. That could cause our terminal to exceed its rating as well. So what does this say? We've passed through steps 1, 2, 3, 4. Everything was looking good. Now, bam, all of a sudden that 12, it's not big enough. It's not big enough because that 75 degrees C rating of the terminal that it's connected to. In which case, what do? Well, we increase the conductor size. 10 AWG copper. Obviously, it's going to be sufficient for the ampacity calculations we just did. It's got more ampacity than a 12. And when we go over to the column that matches the rating of the terminal it's connected to, that 75 degrees C column, we see that our 10 AWG conductor, 35 amps. And yes, that's bigger than our step 3 value of 26.9 amps. So we have to go up one size. 10 AWG conductor will be sufficient. The steps we've looked at thus far are all about safety. These are code requirements for making sure that our conductors can handle the current and the terminals they're connected to aren't going to get overheated and the overcurrent protection device is going to protect stuff. Up next, we look at voltage drop, which is a design consideration to make sure our systems operate effectively. Catch you there in a minute.